Ihor, I have two follow-up questions from your previous section. Number one, you were mentioning biodiesel. There's an adjacent topic to biodiesel, and that is sustainable aviation fuels. How do oleochemicals play into sustainable aviation fuels as opposed to, for example, those made by a Fischer-Tropsch type process? Which one has more utilization right now? And a follow-up question after that is related to your soap discussion. You mentioned potassium or sodium addition, potassium hydroxide or sodium hydroxide addition to your free fatty acid. How does the cation impact the final property of the soap, like potassium versus sodium versus perhaps another cation that we have not mentioned yet?
So I'm not sure if I can answer your first question because I'm not really familiar. How I don't really know how they use that biodiesel in aviation. Um, I know that biodiesel long time was considered as alternative sustainable fuel in Europe. There was time when European gas stations sold biodiesel, and maybe now it's not a big uh, fuel potential in the US. I don't see like gas stations here like for cars. In aviation, I cannot speak about that. You might know more about it. I think the advantage of using biodiesel, potentially using biodiesel as a fuel, is that it gives you a cleaner burn, from what I know, and it's sustainable to some extent. You can harvest your crop, make it into an oil, make it into biodiesel, use it. So you don't have to rely on petroleum to do that. Well, regarding the second question, soaps, that's quite interesting. Fatty acids are highly hydrophobic products, and we use this property for different applications. We can use it. If you ionize the carboxyl on fatty acid, now it becomes sort of amphiphilic, so it has polar group and then this hydrophobic chain. So both ionizations by these sodium and or potassium ions, they are very strong. I think the difference is in the bulkiness of potassium and sodium. Potassium is a little more bulky. In terms of soap performance, I don't have the data to say. I know that potassium soaps are more viscous, and they tend to be um, less hard, if you want to say. And dilution, if you dilute it down to lower concentrations, it will make your more viscous liquid. In terms of cleaning performance, I, I'm not sure. I don't think these soaps are used a lot these days. Maybe for industrial uses, yes, but in household, every time we use soaps, these are a little different than potassium or sodium salts.
Can you describe the difference?
So there are ways to to control the size of the polar head of the surfactant, and the industry came up with a little better options and a little more strong ionization. So when they use phosphates and sulfates and attach them to fatty acids, not to fatty acids actually, they convert fatty acids into fatty alcohols using hydrogenation, probably again, and then convert the alcohols into other products with more polar heads, so it has better um, HLB ratio, and it has better cleaning performance. I think C18, if you think about C18 product, it's too hydrophobic to use it as a surfactant. So that's why lauric acid and alcohol are used as a primary source for commercial surfactants. A
Hmm.
little bit shorter, C12 fatty acid is a better candidate, which actually comes from palm. So it's a fraction of palm oil. They isolate it by distilling palm biodiesel.
So speaking of palm and other types of oils, where do you kind of see the industry going in the next like 10 years? I know we chatted a little bit about alternatives, like odd alternatives, like algae oil, and the ability to modify, at the genetic level, some of these materials.
Yeah, that's interesting. I mean, in the US, you don't have palm, don't produce it here. Of course, everything we import, yes, we can import palm oil and other things, products made from palm oleochemicals into the US. But primarily, focus of the US industry is on soybeans. As far as I can see, you can see those calls for new applications. Um, so the USDA has a lot of calls for new applications, making new products and using soy primarily. And one of the other reasons for that is it you can genetically modify it. So you can there are varieties of soybeans that produce soybean oil, which is a little different. It has a different iodine value, which is a measure of unsaturation. So it's more like you can make oil which is quite similar to olive oil. They call it high oleic soybean oil, and they already use it in the industry. It does not oxidize as quickly. If you look at composition, it has a lot of monounsaturated fat. It's less prompt to oxidation, auto-oxidation, compared to conventional soybean oil.
So I know we touched on it pretty briefly in the beginning, but could you just explain a little bit why oxidation is bad, specifically in cooking oil?
Well, because I mean, these double bonds, they have tendency to catch oxygen. I mean, actually, carbons next to these double bonds are oxidizing quite easily, and they they uh, they tend to catch oxygen, especially at high temperature. So whenever you use it in cooking, it's inevitable. So you will have this oxidation going, and the oxygen reacts in and starts producing different aldehydes, peroxides, and other things, and it's pretty much autocatalytic reaction. So once it starts, there's no way to stop it. You can inhibit, you can slow down this process, and plants synthesize antioxidants like tocopherols, are present in those oils. But every time we clean the oil, every time it goes through the cleanup process, we remove these antioxidants, and then there is no way to protect the oil from oxidation unless you put them back. So every time you use refined bleached oil for cooking, it will oxidize, and then even it will oxidize even in the bottle without cooking. If you just leave it on the shelf for a couple of weeks, months, you start smelling that rancid, right? Rancid smell. It's the first sign of oxidation. And I'm not a big fan of using highly unsaturated oils for cooking. I think I would rather stick with olive oil if necessary, or people say saturated products are bad, but I don't know. It's hard. I don't think there's enough evidence to speak about that. Also, I think using short chain, medium chain fatty acids, like maybe coconut oil might be a good option, but it's personal preferences. I don't know.
I know another colleague of ours, Hunter Brown. He's always he's a health guy, so he's always reading up on healthy oils, and it seems like he's trying a new one every other week.
Okay.
So
So what he
if you're looking
says,
for some data, he may be your guy.
well, I know
So,
many people cannot tolerate certain oils. I was trying to, change our diet and going from one oil to another, but I could not tolerate them.
so since we're on the topic of different health effects of oils and treated oils versus untreated oils, um, we go into a restaurant, you look at the menu, they say no trans fats, no trans fats. Now, I know that was a big health, I guess, debate in the 70s, but can you describe to the audience what trans fats are, where they come from, and I guess how to avoid them in your transformation process when you do partial hydrogenation?
I think you can tell us way more about trans fats than I, because you deal with this very often when you run hydrogenation. In general, I see this process. I mean, oils are nature created them in cis format. So there are different formats of unsaturation, right? So if you think about double bond, there is cis form isomer, and then there's an opposite trans form. So the nature, all the fat oils nature creates, it makes them in cis form. So it's natural for human. It's okay. We can digest it, no problem. Our bodies know how to deal with it. Now, whenever you run hydrogenation or partial hydrogenation of fats, then the catalyst will attack this double bond, will not really attach the hydrogen, maybe, but it might convert the cis fat into trans fat. And I've seen some articles saying that especially it happens at partial hydrogenation. I'm not going to speak about catalysts. You will probably tell. I want you to follow up on that to explain how different catalysts affect this process. But what I've seen, like, let's say if you want to partially hydrogenate the product to reduce the iodine value, to reduce unsaturation, increase oxidative stability, and only partially eliminate double bonds, then that's the highest chance of getting up to 30% of these bonds into trans form. Some catalysts do better job. They only produce like low levels. I've seen 4%, 3, 4, 5%, but others do terrible job. So this I know there are a bunch of health problems related to this because our bodies are not used to transform these types of fats, and they don't know how to deal with that. And I think the industry actually recently I read an article speaking about how the industry figured out to deal with trans fats. So they use oil, hydrogenate it completely, and then they blend it in with unsaturated product, monounsaturated primarily. I think that's the way to go. There might be better options, but at least now we know how we can avoid it. I would stay away from it if possible. Yeah, if you can maybe explain a little bit about different catalysts and what these catalysts do and why this happens, be happy to hear.
Yeah, certainly. I'll do my best. So the fundamental steps of a hydrogenation reaction, just in general, is that you have, or hydrogenation of an olefinic compound, you have adsorption of hydrogen onto your catalyst. So you have H2, which adsorbs onto your catalyst surface. Let's use nickel for an example, because it is the most common oil hydrogenation catalyst. You have hydrogen, which dissociatively adsorbs onto nickel, breaks into two single attached fragments of hydrogen atoms. And then you have the adsorption of your double bond. So it's the double bond that interacts with your nickel surface. The double bond is broken and you have basically both of the carbons attached to the nickel. At this point, the reaction can proceed in a forward direction where you have hydrogen adding to one of those adsorbed carbons. But this reaction can also proceed in the reverse direction. So this cis-bonded olefin on the surface can desorb as an olefin in the trans state. And that's where your isomerization comes from. So as far as catalyst composition, I can't speak to any hard and fast rules on how to avoid the trans fats. But for process conditions, I certainly can. The more hydrogen that is available on the surface, meaning the more hydrogen pressure, the greater availability of hydrogen, the more likely the reaction is to proceed forward, where you have the first and then second addition of hydrogen onto that adsorbed fragment. And when it desorbs, of course, there's no olefin, it's just a fully aliphatic compound. So I don't know if that's an answer, a sufficient answer, but that's kind of a general description of hydrogenation of olefins.
In terms of tuning that catalytic material to do cis-trans, it's a challenge in the field. We've not only run into it on oleochemical applications, but there's other areas in catalysis where that's desirable. Because you mentioned earlier, what do you do when you have a mixture of two components? Generally, you have to do a separation. So how do you do a cis-trans separation, right? Your window of technology becomes really small and very expensive. So it's an interesting area, and I know it's one we've looked into. I can't give up the goods, but there's some interesting options out there. So if we're kind of wrapping up here, can I hit you with a couple of rapid fire questions and just kind of get your gut response, Ihor? And Tate, sure. You can jump in here too. Right? We're just kind of go around the room.
Sure.
Let's see. So, what is your favorite oil to make French fries?
Olive oil. Again, it might be not the best for other people, but I use it everywhere.
Tate, you got a pick?
Probably beef tallow.
I'm with you. If I see beef tallow fries on the menu, I'm in.
Oh, I thought you were talking about a homemade. See.
What's one word you would use to describe the future of oleochemicals?
Oh, my pick is sustainability.
Can you say a little more there?
Renewable.
What is the chief environmental challenge in the oleochemical space? You say sustainable is the direction. What is the current challenge? What is unsustainable, I should say, about perhaps the way its practice now?
Well, I mean, you still need to put a lot of energy, and the carbon footprint of making these products is still quite high. I think that's a challenge, and European countries are looking in that. They are trying to calculate, the carbon footprint of every single product they make and or import. I think that's a challenge because we need to understand how to save, the remaining petroleum, maybe, and just be more conscious, like what we do, how we harvest, and like, especially if the oleochemicals will become our future, and they already become the part of our life. So we have to rely on them. So now we need to understand which oleochemical is the best one, and not only oleochemicals, but just agriculture in general. What's the impact?
Yeah, there's always the food versus fuel debate, right? That was real popular topic, and I know we've chit chatted in the past, but it's really location dependent too, right? Yeah.
Yes, it is. I think we're far from that in the US, but Europeans are very skeptical about it. When every time I meet someone at a conference or just talk to a European company, and the products we offer are oleochemicals, and they keep asking how that impacts the food chain, how that affects food supply. And of course, we make it mostly primarily from soybeans and sugars, but still, that's a question for many people in Europe.
Is there a source of oleochemicals that does not compete with food?
Well, I think there is. I read an article about using algae oils as a potential source in the future for oleochemicals.
How mature is that technology?
Well, it just, you can grow them in a pond. And if you look at like square footage per square acre of that pond, you can make probably more oil or produce more algae oil compared to same area in the field. And that's a trigger. It was a trigger to look at that as a potential source for the future. And of course, the composition is a little different, but it's quite similar to soybean oil composition. I think algae oil is primarily C18. It's a blend of mono and polyunsaturated fats. It also has up to 5% of hydroxyl functional fatty acids, but it's quite similar to soybean oil, with the exception of C16 slightly higher. It's probably 16%, but overall it's quite similar. I think that might be the future feedstock. Who knows?
One more question here. What's your go-to resource for staying up to date in the field? Either catalysis, oleochemicals. What do you like to read?
Well, to be honest, we have a subscription on that Inform, International News on Fats and Oils, which is quite good resource, but I'm not saying that's the only resource I use. I typically I use AI tools. You won't believe it. I just go use AI tools, and whenever I want to find something, just do preliminary search with ChatGPT, and it will guide me in the right direction. Then I'll pull it's hard to read so many articles out there. You have to spend all day trying to find something. So it's a good scouting tool.
Yeah, finding the time to read is tough. Right, I'm usually doing it on a plane or waiting in line for something.
Yeah,
But
especially
outside of that,
new developments in the catalyst fields. They're making new stuff all the time.
well, fantastic, gentlemen. I don't want to cut us short, but this has been great. I'm happy, Greg had a chance to meet Ihor and vice versa, and hopefully there's many more discussions to come.
Thank you for inviting. Thank you for organizing this podcast. I think it's an interesting topic.